Hi, I'm Scott, and this is Ali from K-Scale Labs. We'll spend the next few minutes reviewing our software pipeline that we use to design, train, and control our robots. Here's an example of a trained policy deployed in simulation. Whether you're a seasoned roboticist or a first-time buyer, our aim is to demystify each step and show you just how simple we've made the process. Here we have an architectural diagram describing the entire pipeline, and we'll go over each part in a bit of detail from design to deployment. So let's jump right in.
Yeah, so first things first, you need a robot to do cool robot stuff. And over here, that process starts in CAD design. So here's what that looks like. At K-Scale, we use Onshape to design the robot. And every single link and joint is first mapped out here. Here I have a sectional view, so I can show you what the inside of the robot looks like. So if I just drag this here, you can see the motors in the legs. The big piece in the center is the battery. And if I go up here, you can see the two cameras in the face as well. So this is the inside and outside of the robot that you first have to design in some kind of CAD software. And this mechanical blueprint becomes a single source of truth for the geometry, the mass properties, and the joint limits of the robot. Once you have this, you need to make the robot. So you would either have to 3D print or fabricate the parts yourself, and then you have to get yourself the motors, the drivers, the wiring, and the power distribution for all the electrical stuff. So you can either go do all of that, or you can just buy a ready to run robot from us where we've already taken care of all of that for you. And once you have the CAD design done, you need to turn it into some robot files, which Scott will tell you more about.
Yeah, with the geometry locked in, the next step is getting that mechanical model into software. Using our conversion tools, we can now extract the Onshape data and convert it into a Mujoco-ready MJCF. We also include additional metadata, which contains joint mapping, servo gains, joint limits, friction and inertia, actuator models. And you can see on the left side here in our Mujoco file, we do have a description for the 4 different types of servos that we have in the KBot. And you can see we have friction and inertia constants, some torque ranges, etc. And with that, we now have a complete description of our digital robot ready for training and simulation and in deployment.
Right. So all of these files, they all live inside the Kscale API, which is the software package that can download and manage all of these files for you. So with a single command here, I can simply download all of the KBot files, the MJCF, the URDF, all of the geometry files, etc. And all of the downstream packages that we're going to use for training and deployment, they all use the files that are downloaded from here. So this works as a single source of truth for all of the downstream software packages, and it keeps everything, the simulation, training, and deployment all perfectly in sync. So for example, once you've downloaded these files, you can go look at the MJCF file in here in Mujoco. So this is what that looks like. Here I have the MJCF file loaded in Mujoco, and it loads up the robot. And over here, I can now move the right shoulder, and I can also move the legs. And now, once you have the files loaded in Mujoco and everything's working, then we can start doing more interesting things like training a policy for the robot, which we'll talk about in the later steps. So far we've covered the section kind of over here from the Onshape design to the conversion from CAD to MJCF, and then downloading the files from the Kscale API. And now we can move on to the other sections. Cool.
KOS is our runtime layer, short for K-Scale Operating System, a software package that exposes a single API for our robot control both in simulation and on the real robot. Through that single API, you can push actions, pull observations, manage policies, and update configurations. And because both the simulator and the real robot speak it, every application and tool runs unchanged in either environment. One of those tools is K-Tune, our servo tuning and sim-to-real validator. Using the same API, K-Tune sends identical motor trajectories to both the simulator and the real robot, overlays the results, and flags any tracking errors, helping us both tune the gains on the real system and find discrepancies between the two. We also validate our IMU scaling, orientation, and noise characteristics as well. We update our bots description files via the K-Scale API with any adjustments and improvements that are made, which keeps the bot's information synchronized between training and real deployments. After tuning the servo gains and confirming that the simulated actuators and system dynamics align, we move on to policy training.
Right. So now that we can load our robot into the simulation accurately, we can make it start doing things. We use reinforcement learning to train the robot to do things instead of manually programming it, since this approach scales much better for complex tasks and behaviors. At Kscale, we've made a library to do this called KSim. This is what KSim looks like. It's a GitHub repo, it's open source, so you can go check it out. And we have a lot of nice documentation for it. We have a quick start guide, and then we have more detailed descriptions about exactly how the core logic works. So to get started with getting a robot to do something, you have to define a new task. And the cool thing about this is that this can be its own repository, and in a single file, you can define the kind of neural network you want to use for the robot. So I can, if I search for actor, I can see the actor model. You can also specify the algorithm you're using. At Kscale, we use PPO for the locomotion and all of the rewards. So if I search for rewards here, we can see that we have some basic rewards for things like staying alive, walking in the right direction, staying upright, and so on. Now, KSim pulls the robot description straight from the Kscale API, and then it will spin up thousands of environments. And this can run on a single RTX 4090 or a full cluster. And it will train KBot to perform the given task. Under the hood, KSim is using JAX for training the neural network models, as in computing the gradients and running the optimization to update the neural network weights. And it uses Mujoco XLA for the physics simulation. Both JAX and Mujoco are open source projects maintained by Google. Now, my absolute favorite feature about KSim is that how it automatically plots everything for you. So here I have a few runs that I've been working on for some basic locomotion. And you can see that KSim automatically logs videos of the policy as it learns how to do something. And it also plots basically everything you could ever want. You have all the data that you need here to debug and iterate effectively. For example, let's go down here. One of the basic things that you want to check is that your episode length is generally going up, meaning the policy is learning how to survive longer. And then also if we go up here, you can check that the rewards that you've programmed in are also going up, meaning that the policy is learning how to achieve the desired behavior. So this really lets you see your training run in a nutshell and debug how to make it better. Although sometimes looking at plots after the fact is not enough. You need something that is live and interactive. For this, we've made the Kscale Mujoco viewer where you can, once you have a trained policy or even an untrained policy, you can run it in Mujoco and then have live plots. So here's what that looks like, where I have the robot standing upright and I can see the different rewards being optimized in real time. So I can also now interact with the robot where I can just yank the robot. Sorry, one sec, because I moved the plot, I gotta adjust the x-axis. There we go. So I can yank the robot by just moving it, and you can see that the plots will start to change. So you can, for example, kind of lift the robot up to make sure that, oh, its feet are no longer touching the ground. And then if you have a reward for that, it'll reflect that in the plots. This runs slow because this is running on a MacBook and it's running all the machinery of jacks and the reward calculations and so on the MacBook, which is what makes it a little bit slow. But that transitions us to the next piece, which is that once you're happy with your trained policy, you can export it to a much more efficient runtime file. So once you've trained a policy that you're happy with in KSIM, you can now export it to a K-Infer runtime file, short for K-inference, which allows you to run the policy on the real robot efficiently. You can also test your K-Infer file out in the simulator using KOS Sim, and this is really where the robot description files and the KOS API all come together, and this makes the experience of running a K-Infer file in simulation be virtually identical to running it on the real robot. So over here, I have a K-Infer file running in KOS Sim, and I can actually control this policy with my keyboard. So just joystick WASD, I can press W and the policy will walk forward. I can press S and the policy will walk backwards. I can also go left and right. And that's how you train a policy to walk using KSIM.
Once we've verified our policies run smoothly in simulation, we can now run it on the real robot. Deployment is simple. The robot boots Linux and the KOS overlay, which runs the K-Infer policy and all the I/O on a deterministic and low latency path. So observation to action timing is predictable. KOS also offers a best effort gRPC channel for monitoring and configuration, and all while keeping the entire stack running on off-the-shelf hardware. The deterministic policy to hardware loop you verified in simulation now runs unchanged on the real robot.
Now, after you've deployed a policy on the real robot, you still want to inspect exactly what happened, sometimes frame by frame. We use Rerun for this. Rerun lets you plot various different kinds of data all in the same user interface, making it very useful for debugging and analysis. We can see the IMU in the top left visualized in 3D, like this is the IMU acceleration, and we can also see all the actions output by the policy as well as all the observations fed into the policy. So I can pause here, and for example, I can zoom into this area so we can see more detail about what's going on. The cool thing here is having a complete post-deployment picture of the data all in one place where you can scroll through it frame by frame, which lets you debug issues very effectively. So, okay, there you have it. We've covered everything from designing the robot to training it to then evaluating the deployment. We hope this video overview helped clarify our process and how all the different pieces fit together. And we'd like to thank the open source community, projects like Mujoco, Jax, Rerun, and many more that we can't list individually for making all of this possible. We're really excited to contribute back with some of our tools, and we hope you will find them useful. Thanks for watching.
Thank you. Happy hacking.